Dear learner, I welcome you all to the MOOC on Principle of Electrical Sciences. I am Dr. Sanjay Agrawal, Associate Professor in Electrical Engineering, School of Engineering and Technology, IGNOU, New Delhi. In previous session, we have discussed how power measurement are done in three-phase circuit for the balanced load and unbalanced load. Under this session, we discussed 3 wattmeter method and 2 wattmeter method of power measurement. Dear learner, in this session, we will discuss the power factor, what are the causes of the low power factor, what is the impact of the low power factor, and how the power factor can be improved. So first of all, we have to know about what is the true power and reactive power. So first of all, we are going to discuss that is a true power. The power that is actually consumed or utilized in AC circuit is called true power or active power or real power. It has already been seen that power consumed only in resistance. So expression for the true power can be written as P equal to VI cos phi, where V is the voltage, I is current, and phi is a phase angle between voltage and current, or cos phi is a power factor. The second term that we are going to discuss, that is a reactive power. A pure inductor and a pure capacitor do not consume any power, since in a half cycle whatever power is received from the source by this component, the same is returned to the source. Power that flows back and forth or reacts upon itself is called reactive power. It does not do any useful work in the circuit. The expression for the reactive power can be written as Q equal to VI sin phi. It has been seen that in pure resistive circuit, current is in phase with the applied voltage, whereas in pure inductive and capacitive circuit, current is 90° out of phase. Therefore, it is concluded that the current in phase with the voltage produces a true power or active power, whereas the current 90° out of phase with the voltage contributes the reactive power. Hence, we can write the true power is equal to what? Voltage multiplied by current in phase with the voltage. Similarly, you can write the reactive power is equal to what? Voltage multiplied by current 90° out of phase with voltage. The phasor diagram for an inductive circuit is shown in the figure, where current I lags behind the voltage V by the angle phi. Current I can be resolved into two rectangular components, that is I cos phi, which is in phase with the voltage V, and second, that is another component in the vertical component, that is I sin phi, which is 90° out of phase with voltage V. So you can write the expression for the true power P is equal to V into I cos phi. That means voltage multiplied by the horizontal component of this current, that is I cos phi. So true power P is equal to what? VI cos phi, and true power is measured in watt. Second expression for the reactive power can be written as Q is equal to voltage multiplied by vertical component of this current, that is I sin phi. So reactive power Q can be written as VI sin phi, and its unit is VAR. Third power, that is called apparent power, it is denoted by capital S. It can be written as product of voltage and current, or you can say apparent power S is equal to VI, and unit are written as volt ampere. Now we have to understand the power triangle. So here you can see in the figure, that is a power triangle has been shown here, that OA is representing the true power, that is by the VI cos phi, that is P is equal to VI cos phi. The vertical component AB is representing reactive power, that is VI sin phi, and it is denoted by capital Q. And diagonal part, that is OB, is denoted as a apparent power, and it is denoted by capital S, that is equal to VI. So true power is equal to what? Circuit voltage multiplied by active component of current. This true power produces torque in the motor, heat in the heaters, light in the lamps. Wattmeter also indicates the power. Reactive power is equal to what? Reactive power is equal to reactive component of current multiplied by circuit voltage. And this power is very useful to calculate the power factor of the circuit. And third power, that is apparent power, can be written as circuit current multiplied by circuit voltage. So as I already discussed you that power factor can be defined as cos phi, which is the ratio of the true power to the apparent power. Cos phi or power factor can also be explained as it is a cosine angle between voltage and current. So as I already told you that power factor may be defined in many ways. First, it may be defined as cosine of the phase angle between voltage and current. It may be in leading in nature or lagging in nature. And power factor can also be defined as it is the ratio of resistance to the impedance. Power factor can also be defined as the ratio of true power to the apparent power. Now we have to understand the power factor and its importance. In AC circuit, the power factor may be expressed as power factor, that is cos phi is equal to R upon Z, where R is the resistance of the circuit and Z is the impedance of the circuit. And it can also be termed as true power upon apparent power, as I already explained to you earlier. In the case of the power resistive circuit, current is in phase with the circuit voltage, that phi is 0. Therefore, power factor of circuit is equal to what? Cos phi is equal to 1. So you can say it is a purely resistive circuit, because in case of resistive circuit, the phase angle between voltage and current is 0. While in the case of pure inductive or capacitive circuit, current is 90 degree out of phase with the circuit voltage. That is phi is equal to what? 90 degree. So if you want to calculate the power factor, that means cos phi, so value of phi is 90, that means cos 90 is equal to what? 0. That means in case of pure inductive and capacitive circuit, the value of power factor is equal to 0. For circuit having resistance inductance, resistance capacitance, or resistance inductance and capacitance, the power factor lies between 0 and 1. It may be noted that value of the power factor can never be more than 1. Usually the word lagging or leading is attached with the numerical value of the power factor to signify whether the current lags or leads the voltage. In inductive circuit, current always lags behind the voltage and their power factor are mentioned as lagging power factor, while for the capacitive circuit, the power factor is mentioned as a leading power factor, since in the case current always leads the voltage vector. Now we have to understand the importance of the power factor. So as you know, the power factor of an AC circuit plays a very important role in the power system. Since power of an AC circuit is given by P equal to VI cos phi, if we are talking about the single phase power, so you can write P equal to VI cos phi, where P is the power, V is the voltage, I is the current, and cos phi is a power factor. So by this expression you can write the equation of the current also. This can be written as I equal to P upon V cos phi. If we are talking about the three phase power, so for the three phase power you can write expression for the power P is equal to root 3 VL IL cos phi, where VL is a line voltage, IL is a line current, and cos phi is a power factor. So you can write the equation of the IL also. This IL can be written as P upon under root 3 VL cos phi. From this relation, it is clear that for a fixed power at constant voltage, the current drawn by the circuit increases with the decrease in the power factor. Therefore, at low power factor, AC circuits draw more current from their mains and result in the following disadvantage. And what are these disadvantages? First disadvantage is greater conductor size. That means at low power factor, conductors are to carry more current for the same power, and therefore they require large area of the cross section of the conductor. So if cost of the conductor is increasing, that means economics is coming in the picture of the power system. That means cost of the whole power system is increasing if power factor is low. Second disadvantage is what? Poor efficiency. Poor efficiency means what? Efficiency means what? Output upon input, right? So at low power factor, the conductor have to carry large current, that increase copper losses and result in the poor efficiency. Because if losses are increasing, that means output is decreasing. If output is decreasing, that means efficiency is decreasing, because efficiency is equal to what? Output upon input. Third is larger voltage drop. So at low power factor, conductor have to carry large current that increase the voltage drop IR in the system and result in poor regulation, because for the low power factor value of the current is increasing and resistance of the wire is assuming that it is a fixed. So current is increasing, that means current flowing through that conductor having a resistance R, so value of I multiplied by R is increasing, that means voltage drop is increasing. So if voltage drop is increasing, so whatever the voltage that you are receiving at the receiving end side, it is less. So that means there is a more difference in the voltage from sending end side and receiving end side. So there will be the poor regulation. Next disadvantage is what? Larger kVA rating of the equipment. The kVA rating of the electrical machines and equipment connected in the power system such as alternator, transformer and the switch gear will be more at low power factor, since it is inversely proportional to the power factor. Here you can see that this kVA can be written as kilowatt upon cos phi. So if cos phi is low, that means this value of kilowatt upon cos phi is increasing, that means rating of the kVA is increasing. Now we have to understand what are the causes of the low power factor. So mainly causes of the low power factor is what? Basically it is inductive loads. As you know, in case of the inductive load, what happens? Current lags behind by some angle with respect to the voltage. So if current is lagging with respect to the voltage, that means this phi is increasing. If this phi is increasing, that means this cos phi is decreasing, right? So just now we are going to discuss what are the effect of inductive load on the power factor. So as you know, 90% of the inductive load consists of induction machines. It may be the single phase or it may be the three phase. Such machines draw magnetizing current to produce magnetic field and hence work at low power factor. For induction motor, the power factor is usually extremely low, that is from 0.2, 0.3 at lighting loading condition, and it is 0.8 to 0.9 at full load. The current drawn by the inductive load is lagging and result in low power factor. Other inductive machines such as transformer, generator, arc lamp, electric furnace, etc. work at low power factor also. Now we are going to discuss about the power factor correction, how the power factor can be corrected. So as you know, the cause of the power factor is what? Inductive load. That means current is lagging with respect to the voltage. That means by any means, if we are able to introduce such electrical component which leads the current with respect to the voltage, that means this leading angle can be neutralize the lagging angle. So you can reduce the phase angle between voltage and current. If you are able to reduce the phase angle between voltage and current, that means you can improve the power factor. So as we discussed, low power factor is mainly due to the lagging current drawn by the inductive load. Before we study the schemes of the power factor correction, you can note the following points. First, for pure inductance, current lags behind voltage by 90 degree if it is a pure inductance. And for pure capacitance, current leads voltage by 90 degree. So the solution is very simple. If we use capacitor to draw leading current, and we can cancel the effect of lagging inductive current, hence we can improve the power factor. Here you can see in the diagram, so this figure 1 is showing basically inductive load. Inductive load is nothing but it is a basically, you can say it is a coil which have resistance and inductance. That means the circuit behave like a RL circuit, and in case of RL circuit, what happens? Current lags by the angle phi with respect to the voltage. Now you have to reduce this phase angle between voltage and current by any means. So here you can see in the figure 2 what we are doing. Just we are inserting capacitor across this inductive load. So here you can see that if voltage V is connected across this load, RL load, and capacitor are connected across this RL, so let this current is I dash. So this I dash current will be divided in two current, that is a current I and current I suffix C. So You can also understand this phenomena with help of the phasor diagram. So because here voltage is common for the two branches, right? So just you take the reference phasor as a voltage. So on the horizontal axis you draw the phasor of the voltage. Now here you can say that in case of the coil which have R and L, that current can be written as capital I, which is lagging with angle suppose phi 1, right? Now you are introducing the capacitor. Here voltage across capacitor is what? Voltage V, and it is a pure capacitor. So in case of pure capacitor, what happens? Current leads by the 90 degree with respect to the voltage. Here you can see in the phasor diagram also. This current is denoted by I suffix C. So what will be the effective current due to this capacitive current IC and total current I? So it will be the phasor sum. Here you can see that current is nothing but it is a I dash current. So here you can notice that this I dash is a net current. So here you can notice that phase angle between this current I dash and voltage V is reduced. That means if this phase angle is reduced, that means value of the cos phi is increased. Where cos phi is what? Power factor. So this is how you can improve the power factor just by inserting the capacitor in parallel to this inductive load. Now just we have discussed how the power factor can be improved by simply just inserting the capacitor in parallel with this RL circuit, or you can say inductive load. There are another method by which you can also improve the power factor. So first method is what? Synchronous motor. So just if you introduce the synchronous motor, you can also improve the power factor. This machine basically draw the leading kVAR when they are overexcited, and especially when they switch gear are running idle. They are employed for correcting the power factor in bulk and have the special advantage that amount of correction can be varied with the changing their excitation. This synchronous motor will be discussed after few weeks in detail, how this synchronous motor work and how the synchronous motor work in the leading condition, and how the synchronous motor work on lagging condition. And second method by which you can improve the power factor, that is a static capacitors. So what are these static capacitors? They are installed to improve the power factor of a group of AC motor and are practically loss free. They draw a current leading in phase by 90 degree. Since their capacitances are not variable, they tend to overcompensate on lighting load unless arrangement for automatic switching of the capacitor bank are made. So next method is phase advancer, by which you can improve the power factor. So what is phase advancer? They are fitted with the individual machines. However, it may be noted that economical degree of correction to be applied in each case depend upon the tariff arrangement between the consumer and the supply authorities. Now we will discuss some example on the basis of the power factor and how the power factor can be improved. So first example that we are going to discuss is a single phase 7.46 kilowatt motor is supplied from a 400 volt 50 hertz AC mains if its efficiency is 85% and power factor is 0.8 lagging. What you have to calculate? You have to calculate kVA input, you have to calculate the reactive component of input current, and third is kVAR. So as you know, efficiency can be written as output upon input. So here efficiency is given, that is 85%. So just you put the value efficiency here. So you can write efficiency is equal to 0.85, and output power is given, that is 7.46 kilowatts. Just you multiplied by 1000 to convert into watt. So just you write output power in watt is equal to 7.46 into 1000, and input in watt can be written as VI cos phi. So here power factor is already given, that is a 0.8. So just you put all this value in this expression. So after the rearranging all this term, you can write VI is equal to what? 7460 divided by 0.85 multiplied by 0.8. So after solving this expression, you will get the value of VI is equal to 10970 volt ampere. So this is how you have calculated the VI for this particular motor. Now you have to calculate the input kVA. So input kVA can be written as, because the value is given in the VI, you have to calculate in the kVA. So what you will do, just you divide this VI divide by 1000. So this input can be written as 10970 divided by 1000. So it comes 10.97 kVA. So this is how you have calculated the kVA input. Second parameter that you have to calculate, it can be calculated like this. So input current I can be written as I equal to volt ampere divided by volt, and volt ampere is what? That is already you have calculated, that is 10970, and volts are already given, that is a 400. So after dividing 10970 by 400, you get 27.43 ampere current. So you have now calculated the input current also. Now you have to calculate the active component of current. Active component of current, with help of the phasor diagram, you can write it is equal to I cos phi. So now you have a value of the I, that is input current, that is a 27.43. You have already value of the power factor, that is already given in the problem, that is 0.8. So just you multiply 27.43 multiplied by 0.8, it comes 21.94 ampere. So active component of current is equal to what? 21.94 ampere. Next, reactive component current. Reactive component of current can be written as I sin phi. So you have a already value of the cos phi, so you can calculate the value of phi, as phi is equal to what? Cos inverse 0.8. So just put the value of phi in the sin phi, so it comes sin phi is equal to what? 0.6. So just put the value of sin phi in reactive component of current, that is equal to I sin phi. So it will be what? Value of I is what? 27.43, and value of sin phi is what? That is 0.6. So after the solving, you will get the value of reactive component of current is equal to 16.46 ampere. Third, that parameter you have to calculate kVAR. So this kVAR is basically what? kVA reactive. So this kVAR can be written as kVA sin phi. So you have already calculated the kVA, and you have a value of sin phi. Value of kVA is what? 10.97, and value of sin phi is what? 0.6. So just you multiplied 10.97 multiplied by 0.6, it comes 6.58. So kVAR is 6.58. Next example we can discuss for the power factor improvement. Here you can see the example of 50 MVA 11 kV 3-phase alternator supplies full load at lagging power factor of 0.7. What would be the percentage increase in earning capacity of the power factor is increased to 0.95. So what parameters are given, just you note down first. 50 MVA, that means power is given, voltage is given 11 kV, cos phi is given, that is 0.7 lagging. Now it is what you have to calculate. You have to calculate when power factor is 0.95. So what would be the percentage increase in the earning capacity of the power factor? So how you can proceed? Just you can write down the earning capacity is proportional to the power supplied by the alternator. So megawatt supplied at 0.7 lagging can be written as 50 multiplied by 0.7, because this 50 is given in the MVA, right? You have to convert into watt. So if you multiply by volt ampere by the power factor, so you will get the reading in watt. So megawatt supplied at 0.7 lagging is equal to what? 50 multiplied by 0.7, it comes 35. So megawatt supplied at 0.95 lagging can also be calculated. It can be written as 50 multiplied by 0.95, it comes 47.5. So here you can note down that when this alternator was running at 0.7 power factor lagging, so it was able to generate only 35 megawatt power. But when power factor is improved, that means when this alternator is running at 0.95 lagging, that means it has a capability to generate 47.5 megawatt power. That means how much power capacity, generation capacity of this alternator is increased. Just divide this 47.5 minus 35. So increase in megawatt is equal to what? 12.5. That means if power factor is improved from 0.7 to 0.95, so you are able to generate 12.5 megawatt more power. So the increase in earning capacity is proportional to 12.5 megawatt power. So percentage increase in earning capacity can be written as 12.5 divided by 35 multiplied by 100. That is, it comes 35.7. So here, learner, you can notice that how the effect of the improved power factor. That means if power factor is improving from 0.7 to 0.95, you are able to generate around 35.7% more power in when this alternator is running at 0.7 power factor lagging. Next example, here we can discuss a 3-phase 37.3 kilowatt 440 volt 50 hertz induction motor operates on full load with an efficiency of 89% and at a power factor of 0.85 lagging. You have to calculate the total kVA rating of capacitor required to raise the full load power factor at 0.95 lagging. You have to calculate what will be the capacitances per phase if the capacitor are delta connected. So how you can proceed to solve this type of problem? So advice is just you note down whatever the parameter are given in the problem, right? So like output power is given, that is 37.3 kilowatt, voltage is given, that is 440 volt, efficiency is given 89%, power factor is given, that is 0.85 lagging. So it is very helpful to approach such problem from the power triangle rather than from vector diagram viewpoint. So motor power input, that is P, can be written as 37.3 upon 0.89. That means output divided by efficiency, so you can calculate the power input. So it comes 41.191 kilowatt. Here power factor is given 0.85 lagging. So cos phi 1 is equal to what? 0.85. So by this you can calculate the phase angle phi 1, that is phi 1 can be written as cos inverse 0.85. So it comes 31.8 degree. So you can write the equation tan phi 1 also. So phi 1 is equal to what? 31.8. So tan phi 1 is means tan 31.8 degree is equal to 0.62. So motor kVA R1 can be written as P tan phi 1. This one representing all the parameter at power factor 0.85 lagging. So motor kVA R1 is equal to P tan phi 1 is equal to 41.191 multiplied by 0.62. It comes 25.98. Now similarly you have to calculate motor kVAR at power factor at 0.95 lagging. So motor power input is the same, that is 37.3 divided by 0.89, it is 41.191 kilowatt. Now you have to calculate all the parameter at power factor 0.95 lagging. So this cos phi 2 can be written as 0.95. So phi 2 is equal to what? Cos inverse 0.95, so it comes 18.2 degree. So tan phi 2 is equal to what? Tan 18.2 degree, it comes 0.3288. So motor kVA R2 can be written as P tan phi 2. So it is equal to 41.191 multiplied by 0.3288. So it comes 13.79. So the difference in the values of the kVAR is due to the capacitors which supply leading kVAR to partially neutralize the lagging kVAR of the motor. So the leading kVAR supplied by the capacitor is equal to what? Just you minus kVAR1 minus kVAR2. Value of kVAR1 is equal to what? 25.98 and kVAR2 is equal to 13.79. So it comes 12.19. Since capacitors are the loss free, their kVAR is the same as the kVA. So this kVA upon capacitor can be written as 12.13 divided by 3. Why this 3? Because you are using the 3 capacitor, so kVA per capacitor can be written as 12.19 divided by 3, it is equal to 4.063. So VAR per capacitor is equal to what? It can be written as 4063. In delta connection, voltage across each capacitor is basically 440 volt. So current drawn by each capacitor, that is I suffix C, can be written as 4063 divided by 440, it comes 9.23 ampere. As you know, the current flowing through capacitance can be written as voltage divided by the capacitive reactance, that is IC is equal to V upon XC. And where XC is equal to what? 1 upon omega C, that means this IC can be written as V omega C. Because you have to calculate the value of the capacitor, so this capacitance can be written as C is equal to IC upon V omega. And value of IC you have already calculated, that is 9.23. And this omega can be written as 2 pi f, where f is the frequency and frequency value of frequency is 50 hertz to 2 pi multiplied by 50, and value of voltage is given already 440. So just you put the value of IC, V, frequency, so it comes 66.8 microfarad. So dear learner, in today's session we discussed power factor, causes of the low power factor, what are the impact of the low power factor, and how power factor can be improved. Hope you were able to learn the concept of all the topics. In the next session we would discuss new topic, that is a transformer. Thank you so much.